Let's get started. Okay. Let's get started. Okay, last time we talked about review. Before that, I just want to make a long announcement. Actually, my my goal. So currently, my goal is to give a lecture in Chinese eventually in a few weeks. No, a few weeks, not a few weeks, a few years, in a few years. Sorry, in a few years. But I mean, I cannot immediately jump to that level. So, but if I think I can use Japanese to explain, maybe I will use Chinese. I will use Chinese to explain. Maybe I will use Chinese. 但是我的发音非常差，所以请指出我的发音的错误。对，所以如果我能用中文，现在我的听力还行，但是我的说话不好，所以但是我要一点的提升我的口语，所以如果我可以用中文的话，我用中文。Anyways, Conformal or Takashi identity. Okay, so then we talk about Conformal or Takashi. Free bosons. And then we start talking about two-point functions, and then two-point function free boson is something like so the free boson action is something like this one. So the primary field I use phi, this phi, and then for the free bosons, so I use this colored phi. So this if I use colored phi, this means that the free boson. Okay, and then what we are talking about, and then last time I just a little bit rushed a little bit, try to derive this one. But I just skip some part, so I just want to make the everything consistent. Derive everything. So this one can be understood as phi. So it's after some more. Okay, and then so this is the two-way function, and I will include to derive this one, I include the current for this e to the minus s minus j for ddx. And this is actually can be done for any dimension, any frequency, like this way. So I introduce such a particle with current. Okay. Then you can easily see that this two-point function can be understood. Delta jx2 z like this. Okay. And then I need to set that g. Okay, so like this. Then so that's the case. So essentially, and the action, suppose action can be written as follows: 1/2 ddx ddy y of x and xy phi of y, like this one. This way. Suppose this is the case. In the other example, x y is the sum delta function, 2x minus y, Laplacian is equal to -1/4 like this. Okay, and then to derive two-point function, we just need to use the this equation. And to do this equation, we do the sum shift of the. So we want to write down the shift of the field phi x goes to phi of x plus phi 0. Okay. Shift phi of 0 and then minus s plus dx. So then phi of x, j of x. So that's the I think there's a typo. No, it's okay. I think here is a typo. So this should be plus. I think this should be plus. Okay, and then this is equal to this is it's shifted. If you do that, this shift, what we get is like this one. I will just be schematic ddx. I will be schematic. I will omit the detail phi of y, and then minus phi of x. Phi 0 and minus and then sorry, so this is the same as before, so phi 0 and 1/2 then plus phi 0 x jx plus 5x j. So like this. So essentially what I did is just shift this one to 5 plus, no, this one. From here I just shift, for both shift 5 was, so so 5 like this way, and just expand. And then here, everything here is, I have to include the ddx, or here ddx, ddy, and so on. But I just omit. Okay. Fine. And then if you look at the this, so this shift is okay. So if you shift like this way, it's okay because so in any case we need to integrate over all the field in here. So in the path integral we need to integrate so that all the field here. You need to integrate over, so that even if you shift by 0 of x, it's totally fine. It's totally fine. And then if you take the equation motion of the phi 0, so if you take it, so if you take the equation motion phi 0, delta phi 0, what we get is that like this way, dy axy and phi 0 of y is equal to j of x. Like this way. I think just something strange. What is that? Let's see. So I'm just looking at so if you take dd delta by 0, this will be also affected. Let's see. What's wrong with this? Choose phi 0 to satisfy the condition. Oh, sorry. So the phi 0 can be arbitrary. Sorry. Phi 0 can be arbitrary. So phi 0 can be arbitrary, but so we choose phi 0 of x such that so it satisfies this equation. So we can just take such a shift. That's also fine. Then if you solve this on phi 0 of y is equal to dy. Like this way. So that's that's how we solve. Yeah, I mean, so from here, one can get this one. So can you derive this part? Is it okay? I mean, you just multiply. So we use the factor ddx, ddy, and inverse, whatever. No, sorry, ddy. Ddy is xy and yz. Is delta d x minus. So I use this equation. To get this. So you just multiply this n inverse and integral over one of the variable, so you get this. Is it okay? Okay. Okay. So that's the case. And plug this one. So plug this one back into here. Okay. Plug back into here. And then what you get is that the z of gj is some number and exponential of the half ddx, ddx, dy, xy, j of y, like this one. So like this one. That's the case. So can you, yeah. So plug this one into here. What's left is the, yeah, so what's left is this term. What's left is this term. So this term is very important. And the rest of the term is they somewhat cancel each other. That's how it works. Okay, for instance, if you just plug this one into here, plug this one into here, this one cancels with this one because I mean, A and A inverse cancel each other. So what's left is phi times J, and that cancels with this. Okay, is it okay? Okay, and then of course the first term is left. First term is left. So this n is in fact. So this n is in fact. So this guy is equal to d phi phi, and the exponential minus 1/2 dx. Like this. Fine. That's how it works. Any question at this moment? Is it okay? Any question? Is it okay? Sorry. So I think it's combination of these two. Sorry, combination of these two. Sorry, I think combination of these two. Sorry, combination of these two will give you this point. That's you can see. So if you plug this one into pi here, pi 0 here, you again at the J A inverse J. Okay. So J A inverse J. So if you plug this one into here, you get the J inverse, and they cancel each other. You get the plus 1/2. Fine. Okay. So then it's easy. So it's just normalization factor which cancel with the overall this guy, overall this one, and then so overall this guy. And then also you have this two derivative. So this means that they inverse. So you just do the Gaussian integral of this. Oh no, not Gaussian integral. I mean, you just take a two derivative of J here. Two derivative J here, you get the inverse. That's how you get the two. So therefore, 2-point function is just the inverse of Laplacian in scalar here, pre-scalar. Okay, so that's the case. Okay, and then last time we tried to solve this Laplacian in the Laplacian, so J inverse, and we obtained this one. This one is in fact equal to minus ln x minus y. So that's what we solved last time. So that's what we solved. Okay. Any question at this moment? Okay. So essentially what you need to do is just apply this Laplacian. So minus ln, this is rho square, and then 1/rho. So Laplacian is 1/rho delta rho, and rho delta rho. And this will give you the delta function, like this one. So if you can get this equation up to some coefficient, if you can check this one, so it's horizontal. Okay, so that's how you obtain this equation. Any question at this moment? Okay, so then, so from there, so one can just obtain the OPE of the current field. primary field. So the last time, so that you just take this last time, so the OP of this one is in fact equal to x minus y. Maybe I think now it's only focus on homomorphic part, and then z minus w squared divided by 1. That's what we obtain. So that's what we obtain up to some sign, up to some sign. So up to sign like this one. That's what we obtained last time. And then stress energy tensor is in fact the normal ordering of this one. Of this one. So this is called normal ordering. This one is more normal. I mean, so this normal thing I didn't explain, so this time I will explain. And unfortunately, I missed again. Okay, so that's the case, and I need to explain what the normal order is. Okay, so essentially it's very simple. Normal ordering, just put the here, this one is the creation operator. So we treat, so in this case, all the fields are treated as an operator. Okay? So it's not just function. Okay? It's not just function, it's just operator. And in the case of the what was that? You are doing this exercise, right? K mu, P mu, operator of X. And this is homework. I think due yesterday or next week. I don't remember. So this one. This operator is really an operator. But once it multiply over X, so this guy is not operator. So therefore, you treat X and P. So P and K axial operator. We treat P and K axial operator, not the X. So X is not operator, so that's why X and P and commute. That's what I meant in the lecture. So somebody pointed out, and I thought my lecture was wrong, but that's not true. I mean, unless I use the correct computation relation for this guy, you won't get the correct answer. And you already, most of it, I think you already knew what's going to. That's one. Okay. So that's the case. Fine. So now it's operator. So it's operator. I mean, usually, so if you have this kind of operator, is have a Fourier expansion z to the assumption n minus 1, and is the okay. So like this way, if you have a Fourier expansion, and this guy is the Fock space is a creation annihilation operator, the operator, and of course n greater than 0 is the annihilation. And less than 0 or greater than is a creation operator. Okay. So therefore, so you have to be careful of the order. Okay. Order, because I mean here it's a two operator in multiply same place. Okay, same place. So therefore, you have to be careful about the ordering of the operator. Because I mean they do not commute usually. So you have n is the is equal to n delta n plus n, like this way. Okay, so like this way. It's called 价换关系. Is it correct? Computation relation. Most likely my pronunciation is really bad, but anyway. So it's this one. So you have to be careful about the ordering. So they do not commute usually. Okay. So now, so this means that this normal the equation operator to left. Yeah, annihilation operator to right. That's okay. So that's that. So that's the actually what's really happening. Okay, and then so is it, I don't know. I mean, is this sentence Japanese? 这个是先前验算子 ，is it correct?
Yeah.
And then next is what? Yen. We should. Okay. Then after the break, you should tell me. Okay. This one is 10. Is it correct? I don't know. I think it's. Is it different? 不一样。同样。不一样。好像不一样。Okay. Anyway, so I need to learn each terminology. So you should tell. I mean, in Japanese, this really this one. I mean, this is Japanese, but seems like in Chinese it's different. Okay, then you should tell me the break. Okay, and then, so we have a weak contraction and so on. So we have to do the weak contraction and so on. But weak contraction and so on, I mean, it's better to do it, it's better to do it in an example. It's better to do it in an example. It's not so important to introduce definition and so on. So let's do the example. Let's do the example. So T of Z. So last time, so T phi of W. So that's we did the exercise, and then sorry, alpha of W. So and then we take the weak contraction two way, like this way or this way. And I think I need to multiply some factor here. And then what you get is really get is the del phi of Z, Z minus W squared plus del square phi of, W. W and Z minus W. So that's what we obtained. This is the operator product expansion. Okay, so then so there are two ways of doing the weak contraction, and now so we learned that this way. So the output is the primary field, and what are the conformal dimension? The conformal dimension one. H or delta, I don't know, it depends on notation. Okay, primary field conformal dimension. Because I mean here it's just one. This is here is the place the conformal dimension up here. Okay, so that's the case. And then T of B, T of W is equal to 1 over 4 down 5 of T, down 5 of W. Okay. Then we'll do the weak contraction. Weak contraction like this way. There's the one way is like this way, and the other way, two of them is something like this way. Okay. So it's a bosonic operator. We don't need to worry about the order. And this one, it's easy to see what's going to happen. So this will give you quarter of 1/2 Z minus W to the fourth. Okay, so that's the two ways of this doing that. So this means that the T is already have a high order singularity. It's more than 2, so therefore it's not a primary field. T is not a primary field. And then the other thing is that you can just only take one of the contraction. One of the contraction. Either you do this contraction, or either you do this contraction, or either you do this contraction, and then the other one. And then so then this will give you 2 times. So this one will give you, what's that? C minus W to the square, down 5 of W. Okay. And then you have to be careful on the quotient. So if you take the weak contraction, we should apply this guy. Weak contraction, we should apply this guy. We should apply this guy. So therefore, you get the minus sign. So you get the minus sign. So therefore, at the end, there's a 4 ways to do that. One way is like this way. There's a second way, and the other way is like this way, and the other way is something like that. This way. There's a 4 ways to do that. So you get this. Is it okay so far? Okay. Okay, and then, so let's move on. And this one is equal to, and this guy can be just expanded as the, so this one can be expanded as the minus down 5 of W. So just do the tail expansion. C minus W of square, and then minus down square 5 of W. C minus W. Okay, like this one. Okay, so like this. Okay. So do the weak contraction. If you do the weak contraction, you apply this OP. That's a rule. You have to. Okay. And then you get this one. I just do the tail expansion of this guy. Okay. Tail expansion of this guy. And then you just rewrite this one in terms of stress energy tensor, energy momentum tensor, and what you get is as follows. Okay, so the now this one is equal to 1/2 C minus W to the fourth W of C minus W to the square, and then plus this is del T of W Z minus W. That's what we get. So if you apply the that derivative on the stress energy tensor. So if you have derivative of stress energy tensor, derivative C 2 either of them, that will give you 2, factor of 2, to cancel this 1/2. So therefore, you need 1/2 here, okay? And then you get the fine. So this means that so T of T is not primary here, but conformal dimension, but scalar dimension, conformal dimension is equal to 2. Here is 2. So this part is universal. This part is universal. Any question at this moment? Okay. Okay, so this is TTOPE, and then this term is in fact very important. So this term actually encode. So this term is encode. Most important information. Into this So I mentioned the T of Z of E of Z is the current for conformal transformation. So therefore, if certain conformal field theory, T is always exists. T always exists. For conformal field theory, always you have a stress energy tensor. Or actually, QFT, most of QFT you can have a well-defined T, but some strange cases you can actually. I mean, that is called little string theory. But anyway, so let's not go into the detail. But most of the case, in CFT, definitely we need this 2D CFT, stress energy tensor. So one can always compute TTOPE, it's called TTOPE. And it takes always this form, but the general form of TTOPE is like this. It's easy to understand. I mean, for me, maybe people just call it this is CCAL. I don't like like this. So like this way, and then this is called left moving central charge or holomorphic central charge, whatever you call it. And you can have bar part, so T bar of T and T bar of W is actually CR of C bar plus W bar to the force, and it's the same. So if you have anti-homomorphic bar, so this is the bar, you have a right moving central charge. It depends on notation. Okay. And then total central charge of the CFT is C is equal to C left plus C right. That's the total central charge. Often we consider the non-chiral theory. Non-chiral means the left moving and right moving sector describe the same CFT. Okay. Left and right is not distinguishable. So it's a really symmetric. So it's called non-chiral. But if you study the CFT, 2D CFT, you always encounter left CF moving central charge or holomorphic central charge, and right anti-holomorphic central charge is not equal. That is called chiral CFT. You can distinguish left moving and right moving. So therefore, the theory is called chiral. But in this lecture, we only focus on CL is equal to CR is equal to C over 2 and non-chiral. is called concatenate. Right? Fine. What is the consequence of this TTOP? What the consequence of this TTOP is that the response okay, so consequence of this one is that the one can consider the computation ratio for more than one. But anyway, so before going that, let's think about the meaning of T. So I mentioned T is T of Z times E of Z is a conformal current. So the current of conformal transformation. Okay? So therefore, once you consider the conformal transformation of the stress energy tensor, which can be obtained by reducing Takahashi identity of homomorphic part, DC, E of C, T of C, and T of W. And why we care about the OPE and the only singular part? Sorry, so you should tell me, point me out. This is force. Okay. Force. A single part, we just bring this one into here and do the contour integral. Okay. Do the contour integral. Just bring TTOP into here, the contour integral. And what you get is called 0 to 1 Q 2T of W, then E of W, minus E of W, down T of W. Okay, so like this. That's what you get. And of course, this term gives rise to this term, this term gives rise to this term, this term gives rise to this term, and so on. So this is the infinitesimal conformal transformation. Infinitesimal conformal transformation. Okay, so infinitesimal version of the conformal transformation. So of course, I mean this is 1 over 4, 1 over z to the 4. So now we have a third derivative is involved. Okay, and this is the first derivative because 1 over z squared and so on. Okay, that's how it works. And then it's final transformation. So this one is kind of tricky. So T tilde of W is equal to dW dC minus 2 and T of C. This part is the same as primary field, but because of this term, because of the high order terms, there is extra one. So this is called short-term derivative. W and C like this. So this one is to derive is kind of difficult, but there's a way to do that. Its definition is as follows. So this definition is equal to W triple prime 3, 2. So like this. So this prime is the derivative with respect to z. With respect to z. This is third derivative. So of course here W is a conformal transformation, conformal function of z because it's a conformal transformation. Okay, so it's our and this is the final version of this. Okay, so Okay, any questions at this moment? Fine. Okay, so then let's. So now, so we will do the following thing. So we just do the expansion of T of D at this kind is sum of Ln c to the n plus 2, where n is integer mode, like this way. And then we just want to understand, so this is operator, so this is also operator. Okay, so operator. And then want to know about the computational relation of this. So we want to know about the computational relation of this mode operator. And by using this one. And we know this, so therefore, so this is essentially Fourier transformation. Fourier transformation. And then if you do the expansion like this way, 1 over 2 pi I dc T of z T to the n plus 1 and the at origin. And the quantum at origin. It becomes like this. Okay. So therefore, if you want to have a computational relation between Ln and Lm, you can just have 1 over 2 pi I square dv dw. Sorry, it's offset. So dw on 0 and dw. And then c and wn plus n plus 1 and then z n plus 1 and tc and tw. Okay. That's how it works. So you have to be careful about a little bit about the ordering of the integral. So here we are doing radial quantization. So radial quantization. So therefore you have a c, and at the origin you have a here t of w. We have a t of w here. And then what we need to do is that the operator acts. So you have to do the radial order. So instead of time, so if you go to the cylinder, time ordering become really like this one. So if you go to the cylinder, so time is this one, and time ordering is really from the past to infinity. In the case of this plane, it becomes radial order. The circle is something like this one. Circle is something like this one, and so on. So this is the radial ordering. Time order becomes radial order. Okay. So if you write down like this way, so this means that it's really radial time ordering and radial order. Okay. T of z and then T of w is a really radial. Fine. And what you need to do is do the, let's see. Okay, so here, first you have to have ln. So ln, first act on it means ln is the, sorry, what I'm trying to do. So the first z is outside. Z is outside of this one. T of z is something like this one. T of z. Okay. So this way is the, so if W is in here, so the ordering is here. So T of W is the inside of the orange. So therefore, TW has to be right side. It first acts on the state, and the next it acts on T of Z. Okay. So therefore, this will give you ln action ln, because M is really picked from W. Okay. W from this M. Ln is coming from W part. Okay. On the other hand, ln comes from Z part. Okay. Z part. And the computation relation is like this way. Okay, like this way, right? Is that okay? So the helpful. So minus. So if you have this one, a minus of this one, TZ, you put this one. So you take a difference. Difference means that you take the opposite contour. Okay, we can have an opposite contour. And since this orange part is counter each other because it's the opposite part, and what's left is some other color choke. What's left is the contour integral here. Okay, is it okay? For this one. Okay. So Z has to be integrated over around W, because of radial algebra. Do you understand what I mean? And what's left is the, for W can be any. Okay. So W can be put by using this prescription. Using prescription, one can just rotate over W 0, and you just do the computation. To do the computation, again, we plug this one into here. Okay? And do the integral. And this integral, one has to do, is super easy to do. Do I need to? This integral has to do by using this OP. Here. This OP and plug up into here, and then we need to satisfy this computation relation. What you get is the follows: n minus. I'm not going to do all the calculation. It's not so difficult to perform. C over 12 or 24. N square minus 1, delta n plus m. That's what you get from this computation. Okay, fine. Or in this lecture note, it's just C over 12. Okay, that's another way of writing. So this is the central extension of bit algebra. So bit algebra is this only this part. But now we have a central extension. So this is called Virasoro algebra. Okay, so this is called Virasoro algebra. Any questions on it? Okay. Fine. Okay, so now we consider some radial quantization, and then state operator correspondence. And then inner product of heurispace. Okay, that's we okay. So now, the radial quantization means that the again, so if you consider the operator phi of z, and you have a limit z goes to 0, acts on vacuum, you get the state. Okay. So this is the state operator correspondence we learned already. So this is state operator correspondence. So given the operator, you have a state, corresponding state you have. And then we want to define the inner product in heurispace. And to define the heurispace, what we need to do is that we just take the conjugate. Okay. Map the z goes to 1 over z bar. Okay. So if you take the conjugate of the operator, so at the level of state, at the level of state, inner product is the Hermitian conjugate of the inner product is really phi out is equal to phi in of that. That's Hermitian conjugate. At the level of operator, we need to do perform this kind of operation, because now we need to put the so this point, so whatever. So this one is a unit circle. So this is a unit circle. Then 1. So if you have a phi here, phi of z here, and you just map to the opposite one. Okay. And if this approach to the 0, this means that if you take this z equals to 1 over z bar, so the opposite part, so this is phi of 1 over z bar, 1 over z bar, or it's just a conjugate of this operator, phi of 1 over z bar. It's just that once approach to the 0, it just goes to infinity. It just goes to infinity. So therefore, what you need to define is that the phi of z or z bar into dagger is equal to z bar minus 2h or 2h and 2 delta, whichever is okay. 2 delta z minus 2 delta bar and phi of 1 over z bar. Like this one. That's a Hermitian conjugate one. Here this term is really coming from this conformal transformation. If you do the conformal transformation of the conformal transformation, what you get is that the f of z bar and then dz bar. So in this case, to the minus delta. Okay. Is it the yeah, I think in this case this is the correct thing to do. And then z df of dz is minus 2 delta bar. So it's not conformal transformation, but it's because it's not conformal transformation. This is not conformal. conformal transformation. Because I mean, here it's just an anti-holomorphic. You just take anti-holomorphic. But to define the Hermitian conjugate, one has to take this operation. To take the operation and take limit. So we find out. Yeah, you have to take this kind of operation. So to define the out states, to define out states, you have to take this kind of operation. So this is essentially meaning that so in the radial quantization, so we could take the operator, Hermitian conjugate operator to here by taking dagger here, and then you have to appropriately multiply some scaling factor, and then if you take z goes to 0, this conjugate operator goes to infinity. So now one can act the out space, out vacuum, and that's how you define an out space in quantum computing. And then again, that's how you define the so that's how you define the out state. The consequence of this multiply of this one is as follows. So if you have this phi of z have a following mode expansion, sum of n on z, and then z minus n minus h, z minus n minus h bar, and then sorry, z bar minus n and then phi m and n. Then phi diagram of z and z bar should be as follows. And you just put the z bar here, and minus h, z minus n minus h bar, then the phi diagram, okay, like this one. Okay, so that's the, diagram. So literally, you just take dagger from here to here. You just take a dagger. So here holomorphic z, but it becomes z bar, and z bar becomes z, and then this mode becomes just conjugate. And you just compare with this guy. This is the definition. Okay, so let's do the definition. If you take this one, so z bar to minus 2h to delta, z minus 2 delta bar. Oh, I shouldn't use delta. So now I use conformal to h. Sorry, I think I should change to h. My notation is now h for conformal dimension. Okay, h bar. Then phi 1 over z bar 1 over z is sum of mn. Then z bar m plus h bar, h and z n minus plus h bar. But now we multiply this guy. Okay? Multiply this guy. So therefore, I just take this is 1 over z goes to 1 over z bar. Then they become like this way. But you need to multiply this guy. So therefore this becomes minus, right? Okay? The same thing happens here. If you multiply this one, this becomes minus. And then phi and n. Okay? And then according to this guy, this definition of the Hermitian conjugate, this should be equal. This should be equal. Okay, this should be equal. And if you compare between these two, this means that the phi mn dagger should be equal to phi minus m minus n. Okay, is that okay? So if you be careful, this is just bar. Just bar. So there's no minus sign, but here it is a minus sign. Therefore, to go from one to the other, you have to take the negative mode. If you compare negative mode and positive mode, or vice versa. So this is the Hermitian conjugate at the level of the operator, the mode or mode operator. Okay. Fine. That's how we define the Hermitian conjugate. Hermitian conjugate of the operator. And then now we just consider the Hilbert space. Okay. Fine. Okay, so now consider, we start with the vacuum. So T of Z from 0. So we want to have this kind of like a state operator correspondence of the source energy density. Okay, so to get that limit 0 to 0, this means the sum of Ln C to the n, and it is C plus 2 and acts on 0, right? So like this. Is that okay? So far? And then here, of course, I have to take a limit 0 to 0. So to define the well-defined way of acting this one, taking 0 to 0 limit means that the L, so 0 of C squared plus L1, L minus 1 of C plus L minus 2 minus 2 plus C L minus 3 and so on. Acts on 0. Like this way. Once you take 0 to 0, so this becomes divergent, right? So this becomes divergent. This becomes divergent. So therefore, to take 0 to 0 in well-defined manner, we have to define. Oh, sorry. What I'm doing here? Oh, it's okay. So L n acts on 0 should be 0 when n is greater than minus 2. That's what we need to define. That's how we need to. So that's how we define vacuum. Is that okay? So therefore, state operator by state operator correspondence. So T of Z is the state operator correspondence. What should be the right hand side? This is operator. State is what? What is the corresponding state for T of Z? Under this state operator correspondence. Let's speak up. I think somebody already understood. So this is an operator. So it's an operator. What is the corresponding state? Under the state operator correspondence. You guys already understood, right? Just speak up. Why? If you take zero element of this one, action, what would you get? Good. L minus 2 acts on 3. So this is the corresponding set. Because these are L0, L minus 1, everything acts on 0. So this is you can ignore. And this red part is you can ignore because z goes to 0. So only the part which is relevant is L minus. Okay. So that's the state overrun correspondence. Fine. That's how it works. Okay, I think it's a good time to take a break. I mean, I can talk about Berman module and so on, but if I talk about it, we need to take 10 or 15. I think let's take a break. Okay. 好像我没有用中文的机会，我的中文太差了。So how do you say operator in Chinese? 燕子，演算子。啊，那日语一样。So 现成演算子，creation operator 现成演算子。Annihilation operator how do you say? 颜面啊。页面，演算子 ，OK。So state operator correspondence is 状态，演算子对应。Is it correct? State operator, that's called state operator correspondence. State is 状态。The same. Okay. Anyway, let's take a break. Yeah. 没有，用中文的机会。算谱啊，算谱啊，算谱 ，I see， 明白了。状态算谱对应 ，I see。那用中文上课很远，那现在我的中文达不到那样的水平。哦，没有录音，我忘记了录音，对，我真的粗心大意，所以好多失败。 算复对应，再算对。No. Somewhat, I don't know why I cannot open e-learning right now. I don't know why. Okay. Yeah. Oh. So 作业的节气期限是做完你要交给作业做做完对对做好了。那 也可能今天我要给你新的作业，但是你有期限，两个星期的期限，说明不要着急。两个星期或者3个星期，我考虑一下。那我们继续吗？好的。就the stress energy tensor corresponding to L minus 2, 0. And also this information conjugate is really, this correspondence really the P mu is equal to K mu. So that we already learned last time, a long time ago, already like a few weeks ago. So P mu corresponds to what in 2D CFT? P mu corresponding to what? In 2D CFT. Yes, so essentially it corresponds to L1. Okay? Essentially it corresponds to L1, L1 plus L1 bar. But if you take dagger, K mu corresponds to what? K mu corresponds to what in 2D CFT? So bit algebra. L minus 1. Good. So it's really consistent with this relation. Okay. If you take a dagger of L1, you should get L minus 1. This is the n goes to minus n. Okay, so it's really consistent. So essentially Ln dagger is equal to L minus n. That's the Hermitian conjugate in the okay. In this way, so one can measure something. Okay. Something about Hilbert space. So we can give you, so using this Virasoro algebra, one can just construct the something about Hilbert space, something called or representation of Virasoro algebra. One can construct Hilbert space of the 2D CFT, some basis. So that's called Berman module. Okay, so the Berman module. So now, so if you have a phi is a primary field of conformal dimension H, and then state operator correspondence, we just call it this one is equal to H, and that's the notation I'm going to use like this way. Okay. So now we have phi of v. Sorry, T of v, phi of 0 is equal to H phi of 0 v squared plus the phi 0 of v. That's the of E of primary field. Is it okay? Is it clear? Okay. So then, if it acts on the so this T of v of phi of 0 acts on 0, then this means that this T of v of 0. Okay. Not 0, H bar. Okay. And the right hand side, in fact, is given by H of the square, okay? And then like this. So this is a rough correspondence. So therefore, this means that the so here, so you can just have expansion. Okay. I mean, this is not the right way to derive, actually. This is not the right way to derive, but what I can do is that the, okay, sorry, I think the better way to do it is that the phi of 0, phi of w. If you have this kind of the permutation relation, what you get is that the 1/2 2 pi w dc cn plus 1 like this one. So that's the case. And if you use the OPE of this one, what you get is that the as follows: 1/2 pi I w dc cn plus 1. And here you have z minus w h bar h and phi of w plus the phi of w and z minus w. And this one, like this one. And dot dot dot. It's regular part. And do the contour integral. Contour integral. For contour integral, what you get is that the what you get is from first term we get the h n plus 1 w n or phi of z phi of w. Okay, so that's what you get, and then plus. And then you have just a phi like this. Like this. Okay? Is that okay? Fine. So therefore, if you look at the computation relation between phi L0 and the phi of W, this will get, what you get is that the H times the phi of W, okay, and then this is what's left. And you can act the so you can act the here in vacuum. You have a vacuum and take limit. W goes to 0. Okay, W goes to 0. What you get is that the L0 acts on H is equal to really H. Okay, that's what you get. Is that okay? Okay, so L0 acts on vacuum is what? L0 acts on vacuum. You get what? 0. Okay, 0. So computation relation, we only care about one term, because I mean, if you take the opposite or the acts on it, you get just 0. Okay, fine. So this is how the L0 acts on primary field. So this is our primary state. So in the state operator correspondence, we did already. So this is for primary state. Okay, so let's look at the next one. Okay, so then L minus 1. This one is kind of okay. This one is kind of this one is kind of tricky. So the moreover Ln. So Ln acts on phi of Z phi of W, where n is greater than 0, n is greater than 0. So here everything greater than 0, okay? N is greater than 0, and then how it acts on it to the state is that you have to take W goes to 0, okay? W goes to 0. So therefore, limit W goes to 0 always becomes 0. So this means that the Ln acts on H is equal to 0 when n greater than 0. So that's how the Virasoro mode acts on the primary field. Fine. So therefore, what's happening is that you start with H, and you just apply like this way, and then or L minus 2 acts on H. So this is called level. So this is level 0, level 1, level 2, and so on. These are descendant. They're like the same reason as before. In general, it can only act on P mu L1. Sorry. So you guys just told you wrong. This is a -1 and plus, right? Yeah. So you should correct me. So P corresponds to L minus 1. K corresponds to L1. Okay. So in the case of the high dimensional conformal filtering, only to get the descendant you act on P mu, bunch of P mu. But now we have a lot of mode, infinite many modes. So therefore, these are descendant. These are primary field and the primary state, and you have descendant. Okay. You have a descendant, and so on. This is level 3. Like this way. Like this. Is that okay? So these are okay. So these are called bomb modules. So these are called the bomb module. So the bomb module is the Virasoro algebra representation. So and primary field is essentially analyzed by this one. This is corresponding to K mu analysis 0. In the primary state in high dimension. That is exactly what we learned before. Okay. So now, how about this L0 acts on this L whatever minus M acts on H. How about this one? What's the value of this one? And this one can be obtained by just computational relation. So L minus M L0 plus M L0, so that's the Virasoro algebra. It will tell us acts on H bar, H on H, and we know this one acts as the. Oh, sorry, this is minus M. Okay, so when I use the Virasoro computational relation, is equal to m times L minus. Okay, is it okay? And then this means that L0 axon H bar is what? Not H bar, sorry. L0 axon H is what? H. So therefore this is n plus H. L minus n H. Okay. Yeah. That's how it interact. Okay, so that the level k dependence is the eigenvalue of L0 has an eigenvalue k plus h. Okay. All right. So that's how it works. Okay, and then we often consider the generating function. So generating function. So that's also same. So even if you have a multiple operator axon, that at the end of the day, if you use this computational relation, level 3 descendant is in fact 3 plus h is the eigenvalue of L0. Is that? So. And then, so often we consider so-called generating function. Generating function. So, I don't know. I mean, and the generating function, most likely in Chinese is called 配分冠数. Yeah. So this is trace of Hilbert space of q to the L minus c over 24. So this is the trace of q to the L minus c over 24. Okay. For instance, in this case, the top, the first part, this part acts as q to the h plus c over 24. Minus c over 24. Okay. Okay. And trace means that the trace over all Hilbert space. So therefore, there is a level 1 descendant. So therefore, q h plus 1 minus c over 24. And next is 2 level 2 descendant. L minus 1 square, L minus 2. Therefore, you have a 2. Q to the h plus 2 minus c over 24 plus the next is what? So you have a 1, 2, 3. Okay, 3 level 3 descendant h plus 3 minus c over 24 plus the total. That's how you count. The state. That's how you count the state. But instead of doing like this kind of counting by brute force counting, one can do a very efficient way of doing that. Because it's just a bosonic Hilbert space of Virasoro algebra bosonic. So one can just do the geometric series to construct interaction. Okay. Say, if you look at the L minus 1 part, okay, if you look at the L minus 1 part, it always acts like this way. So it has so you just consider H, L minus 1 H, L minus 1 square H, and the L minus 1 cube H, and so on. Can we just repackage? So first of all, we can just repackage. Everything's overall factor is q to the minus c over 24. That's overall factor. If you consider this part, you have 1 plus h bar. H minus c over 24. 1 plus 1 q plus q squared plus q to the cube plus q to the fourth plus 1. That's what we get. And also, we can consider the following next one, h bar, h minus 2, h, and next is l minus 2 squared, h, and so on. That is, in fact, 1 plus q squared, q to the fourth, plus q to the sixth, plus 10. That's the contribution. Okay? That's the contribution. Coming from the L minus 2 to the power. L minus 2 to the power. Okay. Likewise, L minus 3. If you consider L minus 3, you have 1 plus q to the cube, plus q to the 6, plus q to the 9, plus dot. And in fact, this one is just geometric series. This guy is geometric series 1 minus q. This guy is geometric series 1 minus q squared. If you do the Taylor expansion of 1 minus 1 over 1 minus q, you get this geometric series, and this is also true. And this is the, again, 1 minus q to the q. Then we can multiply. If you can multiply, so then you have a term such like a, so to get this 2, okay? To get this 2, we count q squared times 1, everything 1, or q squared times everything other is 1. So this will give you 2. Is that okay? To get the 3 here, this guy will contribute, this guy will contribute. What else is contribute? Q times q squared. Okay? That is L minus 1 action, and this is L minus 2 action. Okay? If you multiply it together, you get another. Yeah. Sorry, this is still not square here. So L minus 2. So this is the contribution. If you multiply them together, everything, you can generate all the state, the contribution from this module. Okay. So essentially, what you need to do is that you have q to the h minus 0.4 and 1 over 1 minus q to the n and 1 square 1 to the n. That will give you the partition function or generating function, whatever you call it. So that's the case. And this can be written as follows. So PL is a partition of the integer L. So this is the partition of the integer L. Partition. Number of partitions, sorry. Number of partition of integer L. Positive integer L. Okay. Let's look at the 2. Y is equal to 1. 2 is equal to 1 plus 1. Okay. That's only or 2. Yeah, 2 is equal to like this way. There is 2 way here. 2 way to represent the 2. 3 is equal to 2 plus 1 or 1 plus 1 plus 1. Okay? There are 3 ways to do the partition. How to say partition in Chinese? I don't know. I don't know. Anyway. Paper. Anyway. Partition like this way. And then have a 4. 4 is 3 plus 1, or 2 plus 1 plus 1, or what else? 2 plus, sorry, 1 plus 1 plus 1. Yeah, sorry. I was 2. 2 plus 2 and 1 plus 1 plus 1 plus. Okay, the 5 way of doing that. 4 or 3 plus 1 or 2 plus 1 plus 1 or 2 plus 2 or 1 plus 1 plus 1. Okay, so therefore this should be 5. This should be 5. You understand? And this is exactly how the Virasoro mode acts on the state. So 3 plus 1 means L minus 3, L minus 1 acts on the primary states, and 2 plus 2 is L minus 2, and L minus 2 acts on primary state. And so this one is L minus 4 acts on the primary state. Therefore, depending on the partition of the integer, the number of partition function integer is give you the this Jennings function of the Conformal module, or partition function, whatever you call it. Okay. And then so suppose H is 0 and C is equal to 1. Then this one can be written as the data function inverse, like this. So this is a differential derivative data function. So that's the differential derivative data function. That's the. Any question at this moment? Yeah, so far it's super straightforward. Okay, so we know that we start with H, and then we can just normalize H bar is equal to 1 usually. So this is how we normalize the primary state, and you can consider L1, L minus 1 acts on H bar. So this is the descendant, level 1 descendant, and you can take the inner product. For instance, if you take the inner product of H itself, this conjugate, this becomes what? This becomes what? Speak up. So this one is descendant, level 1 descendant. What? Okay, somebody mentioned already. This is 0 because L1 acts on H is 0. L minus 1 acts on left H is just a L1 H diagonal. Okay, and this is 0. Okay, this is 0. Now, so if you take the inner product of the descendant itself, okay, the descendant itself. So if you do the computational relation of the Virasoro algebra, you get the H 2H. I think that's the what you get, right? Oh, sorry, I missed that. Sorry. Okay, let's do it carefully. So this one is equal to L0, 2 plus 0, 12. Oh, 0, no, nothing. Yeah, it's okay. Yeah, 2 L0, H, 12. Okay, so that's how you do it. Okay, is that okay? Okay. How about this? L minus 2. H, L2, H, like this. And what you get is as follows. 4L0 plus 0, 12, 2 times 2 over. So that's what you get. Over H. Okay, so now there is a contribution from central charge. Okay. And this is equal to 4H. Then this is 3 times, so C over 2. Okay. So that's what you get. Okay. Fine. So in general, and the Hilbert space, usually in physics, the Hilbert space, for unitary theory, all the inner product needs to be positive definite. So any state you get ring. So any state you bring. So phi operator should be, we assume, positive definite for Hilbert space. So therefore, if you consider L and L minus n H. Okay, so 0, 12, and so that's what you get from this analysis. So this has to be always for greater than or equal to 0 for n is positive, whatever. So that's the case. So this means that to get this one, first of all, H has to be positive, that's for sure. Okay. Otherwise, no, doesn't make sense. H has to be positive, and also C has to be positive or non-negative. Okay. Because I mean, if C is negative, this is cubic in n. So this is cubic in n. So if n is very big, this term dominant. Okay. If n is very big, this term dominant because this is n cubed, this is n in linear in n, this is n cubed. So this n is big if this term dominant. So if C is negative, the inner product becomes negative. Okay. So therefore, for unitarity, we have to impose this condition. So therefore, for unitary CFT, you need to have a positive central charge or non-negative central charge. Okay. So that's the constraints from unitary CFT. But nowadays, even non-unitary CFT is kind of interesting actually. When C is equal to negative value, so one can consider very, very interesting CFT and a very, very interesting thing happening for negative central charge, and it's a very interesting topic of the current ongoing research. So, I mean, for physical theory, you have to have the central charge positive, but if you look at some subsector Hilbert space, one can have like this kind of like a very specific non-unitary CFT is somehow appear. That is the very interesting part of the. I mean, if you look at that, it's very strange, famous work by 48. It's called 48 n equal to 2 superconformal field. So you can consider four-dimensional CFT, but in addition to that, you have a supersymmetry. So there is some BPS. Okay, so supersymmetry is essentially square root. It's the square root of the translation. Essentially, a supersymmetry square root of translation. And then you can consider some state operator of states which is analyzed by Q. This is called BPS states. BPS states. And if you look at this BPS states, it is exactly the representation of this Virasoro algebra with negative central change. So this kind of thing happens. And also, we will see in due course, there's a famous work by the most famous Chinese physicist, Li and Yang. Liang model, Liang motion. I think, is it correct? Li is correct, Li? Yeah? Is it different? Sorry, so this is G. Sorry. Oh my goodness. How do you write? No what? Oh yeah. Motion. This so yeah, we will study the Virasoro algebra, especially representation of the Virasoro algebra. At some point, we will see some null states and so on, and we encounter so-called minimum model of the 2D CFT, and then in minimum model has also unitary CFT and non-unitary CFT, and Liang model is really corresponding some two-dimensional lattice model with the imaginary magnetic field. So it's not the how to say it. So therefore it's not unitary theory, but because it's imaginary, we cannot construct an imaginary magnetic field. But in theoretically, one can construct such a model, and then that is called the Virasoro minimum model in 2,5. So that's the non-unitary part. So therefore, even C is negative, there is some interesting thing going. So you don't need to throw away the non-unitary. Any question at this moment? Okay. If not, I will talk about the free boson free fermion. Okay. So in the due course, my plan is to do the free boson free fermion. Free boson and the free fermion. Okay, free fermion. And then after that, we'll go to minimum model. Okay, minimum model. That's most important to the safety we will encounter. This is in Chinese is really the same. 最小模型. Is it translated like this way? Is it the same? Okay. Okay. 最小模型. And then after that, 后我们学习 IC 模型 ，IC 模型，我们学习 IC 模型，对，最重要的是说Kramer's one， 这个是对语型。对语型 ，So Kramer's one 对语型，我们学习，然后what was that? On side. This one I don't know how to say. Exact solution. I think this is in Japanese this one, but maybe Jimmy is it same in Chinese? No? Jim Brown, maybe here is something else. Okay, 金雀雀 ，OK, whatever. OK, 然后我们that's a plan, so 拉到金图 model. So essentially, analysis model is a free model with potential. It's just potential. They have a potential with potential. Potential, and then we'll consider our RG flow and thermological. C. 这个是我们的计划，这课程的计划。接下来我们学习接着的内容。So it's going to be much more interesting. I mean, free programming is not so much, but after that it's going to be much more interesting. So looking forward to it. So far it's just we are doing really basic preparation. So important thing is the question is using conformal invariance, what we can learn about physics. That's the most important thing. So all those conformal transformation, Virasoro, algebra, and so on, it's also just preparation. What we want to learn is some physics. Okay. How do you say in Chinese in boson? Ferm is like a firm. Boson is also boson. Anyway. So we will consider free boson. Free boson, 自由 boson. 自在 boson. Same? Okay. Okay, free boson. So the action, so I already told you. S is equal to 1/8 pi. I mean, this one is just, I mean, for after this part, it's really basic. So interesting part is this one. So this one 更有趣的它有意思。Okay. 准备，预习准备。So we are doing this, we just keep doing preparation. So it's for interesting part. Okay. I mean, so we are still doing preparation. So you have to be like an interesting part is coming from after prepare everything. Okay. Okay, so that's so this is the action we consider for free field, and then again we consider the cylindrical space. Okay. Cylindrical space. So therefore we just impose this condition. So therefore, circumference is the L. So this is X, and this is T. X and T. So the circumference is L. Okay. 圆周长是 L. And then Laplace equation or equation motion is that this one by x. So that's the case. So this is the equation motion in Minkowski space-time. I think Minkowski and so on, it's not so important. I mean, so here you can decompose like this. The equation can be written. Del t is del x by x. Okay, so so this one. So the phi has to be the function of the phi has to be function of x minus t or x plus t. So if you can write down phi like this way, this satisfies the equation motion. Because I mean, this one is annihilated by this guy, and this one is annihilated by this one. So therefore, if you just have this kind of factorized form, one can just have it satisfy the equation motion. Okay, that's interesting. And I forgot to mention something. Here, after that, conformal block. This one I will include in between, the middle of I don't know how to translate the conformal in block. How to say? Concha. Anyway. So and if you use a model expansion, you have this one. Have the 2 pi L pi 0 x minus t plus minus x plus t this way, and then sum of so if everything like factorized like this way, it will satisfy equation motion. And also, this is just a model expansion. So therefore, so here it's just a Fourier model on the cylinder. You have to do the Fourier model in cylinder. So if you just go x goes to x goes to x plus L, it has to be equal to. You have to satisfy this boundary condition. Okay. So this is the only solution one can have. It's easy to do. I mean, x goes to x plus L, it just shift by plus this integer shift. Okay, 2 by integer shift, that doesn't do anything. And also x counter here. So x counter here, so you don't need to worry about this periodic boundary condition issue. So this is the most generic form of this. So then this should be replaced. The mode expansion with this boundary condition. So now we treat and do the canonical quantization. Canonical quantization. So if you learn QFT, so this is the first things to do. So if you just do the phi and conjugate field can be just defined as a del S. It's just momentum of phi. And this is just a 1/4 pi del T phi, like this way. So this is a conjugate field. And then I call it, this is something like a momentum field pi. Okay? And then, so canonical computational relation, you have to impose like this way for free field. I mean, this is just very standard. X minus y, and otherwise they commute. So the phi. I'm not going to write down everything. And it's equal to pi. It's quite important. So like this. And this is equivalent to saying that so now we treat this phi and pi are operator as the ordinary quantum field theory do. So therefore these modes are also operator, become now operator. Okay. So the consequence of this canonical canonical quantization, what you get is a mode commutation relation. And the bar does not talk to each other. So and the bar does not talk to each other. So that's I mean, it's just a Fourier transformation of this computation relation. I mean, everybody has to do. And then one has to be careful here. So I get rid of n equal to 0 because it's diverging here. Okay. And n equal to 0 part of A is actually called pi. It's a momentum. Okay. It's called 0 mode. So this is the center of mass motion of phi. Okay, so the average position of phi. Okay, average position of phi, and this is momentum. So therefore, okay, so this position of the momentum will give you this standard way of doing computation relation. I mean, this is if you never take the QFT, never done this computation, you have to really do the computation. Otherwise, anyway, this is number one, lecture one, number one in the quantum field theory. Okay. So. Fine. And I mean, everything you learn in the quantum physics course, or what I'm going to say is everything is the you learn from quantum physics course, and then what you need to do is define Hamiltonian. So I mean， 这个内容你们已经学它了，所以 it's going to be boring， 非常无聊的。So 内容，但是我要学这个。I mean, this is just a what was that? Pi times phi minus Lagrangian. Lagrangian? Oh, okay, Lagrangian. So this is the Hamiltonian density. And the Hamiltonian just integrate over this one. The Hamiltonian is equal to integrating using the for special surface. You have to integrate over this Hamiltonian density. This is phi t square w dot plus phi x phi square and w dot. So this is, you have to impose this normal ordering like this. Okay. And plug this one into there, and then this is also a very standard one. 2 pi L pi 0 square plus pi over L sum of L minus n and the normal ordering. And the whole people and more. Okay. So that's exactly what you learn in the quantum computer course. Okay. And then anyway, so if you don't learn, don't worry. I mean, you can just do step by calculation, you end up with this result. I mean, if you haven't done it, 绝对你要 Anyway, you have to do this computation, but once you're familiar with it's going to be boring. So the Hamiltonian computation ratio, if you use this one, if you use this computation ratio, what you get is 2 pi over L and then m minus n. So therefore, if you want to make it simpler, you set L is equal to 2 pi. L equal to 2 pi is just a greatest one circumference is L equal to 2 pi. So therefore, you can ignore all the L here. I mean, if you set L equal to 2 pi, everything becomes simple. Anyway, so that's the normalization to make it simpler. Okay. Fine. Okay. So that's the case. So therefore, from here, one can easily see that if you start with the 0, m should analyze 0 when m is the positive mode from here. Okay. Because I mean, otherwise, if m, that's how it works. Okay. That's how it works. Because I mean, otherwise, negative energy will show up. Negative energy will show up. I mean, here is negative m, and m is positive. Means only negative has the positive energy. Okay. And the positive mode have a negative energy. So unless this analysis 0, you get the negative energy. So for unitarity, from unitarity, this is already the consequence. Fine. So then let's move from cylinder to the the plane. So we use the T goes to minus minus it, so this becomes minus it minus x, and then minus it plus x. Okay. Fine, and then we just multiply. So therefore, let's see. Okay. So I think there's some notational mistake on it. Wait a sec. Just a moment. Yeah, so it's okay. So W is IT, T minus Ix, and W bar is to T minus T plus X. If you do that, this part will become e to the minus 2 pi and W over L. And this one is the W bar. And here it becomes W, and this becomes W bar. And if you multiply minus I here, okay. And then this becomes, oh, sorry, this should be plus. This should be. So that's the change. And then from there, so we need to do the online transformation. So to go to the cylinder, so this is the cylindrical, Euclidean cylindrical coordinate W to the complex planes Z here, Z here, Z here. What you need to do is that Z is equal to e to the 2 pi W over L, and for Z bar is equal to e to the 2 pi W bar over L. Fine. Okay. So then once we rewrite this one in terms of Z phi of the plane Z and Z bar is equal to as follows. I mean it's just for Ln Z bar plus over N Z minus N plus N bar Z bar plus N is not zero. That's the whole expansion. Okay. So then, the phi of t is in fact have a following beautiful form, where a 0 can be identified by 0. So any question at this moment? It's very super straightforward. So of this. Now we consider two-point function. So we go back and forth and like a cylinder, and also this plane and back and forth. We will see many. So here, as we will see in the free field, free boson. So here you have so-called finite size effect. So the spacer finite size effect is that the so here. So always the space length is L. Okay. So it's space length L. Whereas here is the radius. As the radius grows, the circumference will grow. Okay, as the radius. So therefore, we're going to simply define the energy at each time. But here you can just define. So therefore, you have something called finite side effect appear in this set, and they are related by conformal transformation. That we'll see. So now we consider some tuple function for two operator. So phi of t and phi of w. You consider this one and just plug this one into this one into here. What you get is as follows: sum of 1 over n and then n c minus n m minus 1. Okay, so that's what you get from this. Okay. Fine. So then this one is non-zero. Okay. So this one is non-zero only when sorry. So this one. So if you computation of the derivatives, so computation relation between these two, m is equal to m delta n plus mz. That's the computation relation you will get. Therefore, the non-trivial part is really coming from n is equal to n plus m is equal to 0. Okay, non-trivial part always come from here. Okay. Otherwise, if this is a positive mode, this analysis vacuum. Okay. If it is negative mode, if you just do the commutation ratio without this one, well, if n and m, if you add them up, it's not 0, you can freely commute. Okay. Because it's the right hand side 0 always. Okay, so therefore, if it is negative, if they are not equal, you can just move to here and it just annihilate to the left vacuum. Okay, left vacuum. So the important part is only come from n plus m is equal to 0. Okay, n plus m equal to 0. If you do the computational relation, you always get the following thing. So n is greater than 0, 1 over w, and then z. What was the best way to present? W over z. W over z plus w over z squared plus w. Okay. So that's what you get. Sorry. I think. Anyway, so that's what you get. Okay. So when n plus m equals 0, and then say m is equal to -1, and then n is equal to +1, you get this term. Okay, you get this. Is it okay? Is it okay? And this is coming from m equal to -1, m equal to -2. And so on. Is it okay? Because m is equal to -1, this is w, right? W over z. W over z, and the extra term I just fucked out 1 over w. And then a1, a-1, this one is equal to how to say? If you use this one, you get the 1. Okay. You just get 1. Because here it's just A minus 1, A1 plus the bracket. So this is just 1. And this is 0. This is 0, and this is the normalization in this form. Like this. And you just do the same thing. So therefore, this will give you the following term. W over C minus 1 minus W over C. So you just do the geometric series of the denominator. Geometric series. You just do the Taylor expansion of the denominator, you get this one. And this is equal to 1 over C minus W. Okay. Fine. So therefore, so then if you take a derivative of this one, so del phi, like this. Okay. So this is consistent. If you take a derivative of this one, what you get is before. Okay. What we get before from using this triangle equation, take inverse, and then just integrate over, we get this one. We get this result, and this is consistent with what we obtained before. Okay, so at T of Z, we learned this is minus 1, and normal ordering of del phi and del phi of Z. Okay, and then we can plug this one into there, and then what you get is that the 1/2 sum over n. Like this. Okay. So therefore, if you we know this one have a model expansion of Ln Cn plus 2, and is integer. From there, we can conclude that the Ln is equal to 1/2 m in integer normal ordering n minus n, and L0 is equal to sum over n is greater than 0, n minus n, and n plus 1/2, like this. Is it okay? Oh, it's already this. Fine. It's a good time to stop. So this is a relation between Virasoro free field. So Virasoro mode can be written in terms of the free boson mode in the Fourier expansion. And anyway, so that's this relation only holds for free boson. Okay, and then we will learn a bit more about the free boson, and then move on to free parameter next. Okay, let's stop here. Okay, if you have a question, just tell me. Today it's kind of elementary, but we prepare for interesting part. Okay, so 那我们继续吧。Which one? Oh, where?
Upper formula, the means the 0 volt and 5 0.
Sure.
Yeah.
Yeah, that's A0. A0 action vacuum is what? A0 action vacuum is 0. I'll try to remember. Yeah, so A0 action vacuum should be 0. So the vacuum should be 0. Or yeah, it should. It should. It's good for the 5. Yeah. A0 should act on vacuum in 0. So that's why. That's why you don't need to include 0 here.
Okay, so yeah.
如果你用，你知道，中文写的共性腔的书本，请告诉我，我可以中文的 terminology。对，反正就是我一点一点进步我的中文的水平，所以那现在我不知道任何 terminology 词汇没有词汇，共性腔的词汇，所以请告诉我好的。
The rating function of the verb or whether it's a vector h minus c over 24. I don't know where is c over 24.
So my definition is this base of h bar q not minus c over 24. That's my definition. I will explain this one. So next time we will learn that this one will appear for cylindrical space. This one will appear 0 point energy. 0 point